and can be turned off directly by the host if it is deemed quite disturbing. When entering Zoom meetings, participants and related parties must turn on the video. It is allowed to turn off the video if there are signals or network problem, or it is interfere with the smooth running of the Zoom meetings. Participant can use the chat room to interact with a fellow participant for the needs of the event by using polite and courteous language. 6, participants are not allowed to say rude and disrespectful things. And 7, participants must follow the applicable rules. Now, I would like to humbly ask all of our participants to fill the attendance form on the link sent by our committees in the chat box. Before we officially start the event, I'm going to briefly read to you the rundown of today's event. Firstly, we are going to listen to opening remarks from Dr. Idham Darussalam. Afterward, we will begin today's lectures from Professor Commeiras, Professor Banik, and Dr. Palermo. And lastly, there will be closing speech from Dr. Idham and Professor Quatriana. Okay, now we will proceed to our first agenda. Dr. Idham Darussalam from Universitas Gadjah Mada will giving the opening remarks as the host of WCP program. Dr. Idham, the time is all yours.
Okay, thank you, Mas Fadli. So, ladies and gentlemen, please allow me to introduce you about our program. So, okay, I hope that you can see my slide. So again, I would like to welcome you all to our world-class professor program in 2021. So this program is organized actually by the General Directorate of Higher Education from the Ministry of Education, Culture, Research, and Technology of Republic of Indonesia. And today we have a great opportunity to have a world-class professor program with the theme of green chemistry approaches for the efficient synthesis of nitrogen heterocyclic compound. So in this case, we have a special world-class professor invited one. So we have Professor Luron Kamaras from Aix-Marseille University, and me as the host is Dr. Idham from Universitas Gadjah Mada, Indonesia. So please allow me to give you introduction. So this program, the objectives of these programs are to improve and strengthen international network through world-class professor program between Universitas Gadjah Mada and the widely known abroad university, for example, Aix-Marseille University in France. And also, we would like to improve the research quality, especially in the field of organic chemistry, through the research collaboration. And then we would like to increase the capacity and knowledge, insight, skill of the people from the Universitas Gadjah Mada. And we would like to improve the quality and the quantity of the scientific publication from Universitas Gadjah Mada through the joint publication. And at the end, we would like to increase the rank of our university in the world university rank. So to do so, to achieve the objectives, there are two main activities. The first one is fine-tuning publication, and the second one is the guest lecture. For the fine-tuning so this is the schedule of our program. So we have started our program since 6 September 2021. And now we have already arrived to the last session, which is in the guest lecture number 4. So today is 19 November 2021. So this is the last session. So for fine-tuning publication, we have already do the fine-tuning publication for 15 draft publication. So in this case, the speakers are Professor Commeiras and me, and also Dr. Heni Herawati. Yeah. And for the guest lecture series, for your information, we have 4 guest lecture. So the first one, we have Professor Black from the University of New South Wales, Australia. as well as Professor Yujiro Hayashi from Tohoku University in Japan. The second guest lecture at 29 October 2021. The lecture was delivered by Professor Khairuddin from Universitas Malaysia, Professor Rawat from University of Delhi, India, and Professor Patel from the Sardar Patel University in India. Last week, we had the guest lecture number 3, and the guest lecture was delivered by Professor Commeiras, from Aix-Marseille University, and Professor Cravotto from Università degli Studi di Torino, Italy, and then Professor Traye from Université Savoie Mont Blanc in France. And today, it is our great pleasure, to have 3 speakers here in this session, today's session. So the first one, Professor Commeiras from Aix-Marseille University in France, Professor Banik from Prince Mohammad bin Fahd University in Saudi Arabia, and last we have Dr. Palermo from Universidad Nacional de La Plata, Argentina. So for information, these activities was followed by the students, researchers, lecturers, and even teacher, and also the employee from university, research institute, senior high school, industry, and a non-governmental organization. And the participants come from Indonesia, Japan, Nigeria, China, Pakistan, Thailand, France, Italy, and Turkey. And please allow me to introduce our invited world-class professor. So he is Professor Luron Kamaras. So he did his PhD entitled Total Synthesis of Permanent Isolated from Colourberta Algae. And then now he is responsible of the Master of Chemistry in the Aix-Marseille University. And he obtained the full professor since 2018. And then his research of interest is development of new methodologies, including the formation of polycyclic complex structure, as well as total synthesis of natural products and the molecular of interest. So without further ado, I hope that you enjoy our last guest lecture today. So have fun. Thank you very much.
Thank you very much for the warm welcome, Dr. Idham. Now, before we proceed to the lecture session, let us all have the photo session first. So please open up your cameras and put your best smile. Okay, there are one slide. So 1, 2, 3, let's smile. Okay, that's all. Oh yeah. Okay, with the end of the opening session, we will now begin to the lecture session. In these lectures, we highly encourage you to have an active discussion and ask questions regarding the addressed topics. To the participants who attend via Zoom meetings, you may ask your question via chat box or ask directly by enabling your mic or raise hand features. For participants who watch the live stream via YouTube, you may ask your question through the comment section instead. Questions using Bahasa Indonesia and English are both accepted, as I'll be glad to deliver your question to the honorable speakers. Since Professor Commeiras are already here, allow me to introduce Professor Commeiras from Aix-Marseille University, France. Professor Commeiras received his PhD in organic chemistry from Université Paul Cézanne in France. His research interests are development of new methodologies, including the formation of polycyclic complex structures and total synthesis of natural products and of molecules of interest. Professor Commeiras has been a full professor at Aix-Marseille University since 2018 and has been appointed as head of Master of Chemistry program since 2013. He has at least 37 papers and peer-reviewed journals and still counting. He has been involved in many research networks, with the most recent is as co-coordinator of Amidex projects. from 2017 to 2021. It is an honor for all of us to be able to be here and learn from Professor Commeiras about from small heterocycles to complex system, a survey of gamma hydroxyl atoms chemistry. Without further ado, let us give a warm welcome to Professor Commeiras.
Thank you very much.
Okay, Professor, for the next 40 minutes, the time is yours. And I'll be sending the reminder via chat box after 30 minutes has left and 10 minutes are left. Thank you.
Okay, I will share my screen.
Yeah, you may.
Okay. Okay. Tick, tick, tick. Okay. Everybody can see my whole screen? Yes.
You can see it, Professor.
Okay. So thank you very much for this kind presentation. And I would like also to thank Idham for the invitation to be part of this World Class Professor 2021. It's a real honor for me to be with you today. So today I will give my second talk about the gamma hydroxy lactam, their preparation and also their reactivity. This work has been done at the Aix-Marseille University. But before to start with these topics, I would like just to finish my last talk because the last week I unfortunately can't finish my work. I was too slow. So okay. Just to remind what I said. So that last week I said I show you that it was possible to prepare gamma alkylidene butenolide thanks a sequence including a free palladium Sonogashira cross-clopping between beta halogenated acrylic acid and terminal alkyne. We have shown that this methodology allows us to have a large library of gamma alkylidene butenolide, whatever the nature of the substituent at the beta position, at the delta position of the gamma alkylidene butenolide, but also we can also work with alpha halogenated, alpha beta dehalogenated acrylic acid to prepare more functionalized gamma alkylidene butenolide in a second step. After we work on the reactivity of the exocyclic double bond in a special objective to do some spirocyclic compound. And so we try to work with the exocyclic double bond to have donc, the corresponding spirocyclic lactone moiety. So we start to work with the 5,6 spirolactone. And for example, we did the 4+2 cycloaddition reaction between this gamma alkylidene, this benzocyclobutane, sorry, and this exocyclic double bond of this gamma alkylidene butenolide. And when the endocyclic double bond is substituted, we are able to obtain the corresponding 5,6 spirocyclic compound. And after we did some post-functionation to access natural product or the system rings of natural product. We have also shown that without substituent onto the endocyclic double bond, we were able to obtain the corresponding naphthoquinone furanone fused compound an interesting target, since we can find also this kind of scaffold in natural product. Another way to access this 5,6 spirolactone compound is to use 2+2+2 metal catalyzed cycloaddition. And we have two interesting results, starting from an intermolecular reaction. We're able to obtain the corresponding 5,6 spirolactone moiety by using a cobalt catalysis, but by using an intramolecular reaction, we never observe the formation of the 5,6 spirolactone moiety, but the formation of this cobalt-3 complex, which bicyclo 322 nonan core. And just to finish the post-functionation of this gamma-alkylidene butynolide, we have been also interested to the formation of the 5,7 spirolactone moiety. A scaffold we can also find it in a natural product. Here you have an example, which is micrandilactone C, which has very interesting anti-HIV properties. And actually, the best way to access a 7-member ring is to use a 5+2 cycloaddition reaction. Okay, and in our case, we study this kind of cycloaddition, the 5+2 cycloaddition, in inter and intramolecular fashion with this 1,3 dipole, which is actually a carbonyl halide, which can be obtained by the decomposition of this diazo compound, and the exocyclic double bond of this gamma-alkylidene butynolide as dipolar refill. So we start our investigation with the intramolecular fashion. So we synthesize this compound in which the precursor of the O1 dipole is linked to the gamma-alkylidene butynolide. And when this diazo compound is subjective to a catalytic amount of rhodium catalyst, this rhodium acetate dimer, we were able to synthesize this 1,3 dipole, this carbonyl halide, this rhodium carbonyl halide, and this 1,3 dipole could react with the exocyclic double bond to give the corresponding spirocyclic compound. And in this reaction, we are able to obtain this tetracyclic compound with good yields, as you can see after we have a discussion, and in which we observe the formation of 1, 2, 3, 4 stereogenic center in one step, and in this 4 stereogenic center, we can observe 1, 2, 3 tetrasubstituted center. And this reaction is totally regioselective. This cycloaddition takes place only at this exocyclic double bond. And also, this reaction is totally diastereoselective, since we observe the formation of only one diastereomere. So, as I said, this reaction works well. The yield are good to excellent. We can work with different substituents at the beta position of the gamma-alkylidene butynolide. We can add methyl, methoxymethyl. We can work without substituent also. We can work with different nature and length of the tether between the 1,3 dipole and the gamma-alkylidene butynolide. We can have all 5 carbon member tether, and also a all carbon 6 member tether. And also we can have a furan tether between the two partners. And when we work with the furan tether, as you can see, we're able to access to this tricyclic core of the bromine F, which is also another natural product. Concerning the heteroselectivity of this reaction, we observe two kinds of heteroselectivity, even if we have, for each case, only one gesteromer. And this heteroselectivity depends on the length of the tether. Indeed, when we work with a 5-member tether, here you have the transition state, we observe an endo approach between the two partners in which the two oxygen are in the same plane. As you can see here, the two oxygen are in the same plane. And when you work with a 6-member tether, you have an exo approach in which the two oxygen are in two opposite planes. Here we have the oxygen up, and here is down. Okay, so this is for the intramolecular cycloaddition. We try also to do the intermolecular cycloaddition, and in this case, this is a more challenging reaction, since we have a non-symmetrical dipolarophile and also a non-symmetrical dipole. So you can have two big challenges, which have the regioselectivity of the reaction. That means that the cycloaddition can take place at the exocyclic double bond, okay, or in the endocyclic double bond. And for each case, you can have a different orientation of the lactone, this orientation or this orientation. And also for each cases, you can have an endo or an exo approach to give, for example, these two gesteromers. So at least from this cycloaddition reaction, intermolecular cycloaddition, we can have up to 8 different products. So we did this reaction with some modification compared to the intramolecular reaction. We have to add the diazo compound with a slow addition with a syringe pump to avoid the formation of the dimer of this diazo compound. And with this reaction, we are very pleased to find that we only observe one compound. So that means that this reaction is completely regio and selective. The yield of the reaction is lower than previously, but they are acceptable to compare to the complexity of this reaction. And also, this reaction is completely selective. In this case, we're able to obtain the Spiro 5,7, the spirocyclic compound with three cycles, and in which we're able to construct 1, 2, 3 tetrasubstituted stereogenic center in only one step. For this reaction, as I said, we only observe one gesteroisomer, and the gesteroselectivity of this reaction is an exo approach of the dipole to the dipolarophile, in which the two oxygen are in opposite plane. So for this reaction, we can work with different substituents on the 1,3 dipole, such as methyl or protected alcohol, for example. So here, this is some selected example. And we can also work with different substitution on the gamma-liquidine butyronide, methyl at the alpha and beta position, or only at the alpha position, or only at the beta position, or also without any substituent. Okay, so this is the last study I will present you today. We did also some conjugated addition of couplet reagent onto this gamma alkylidene butynolide, a regioselective 1,6 addition, but I won't talk about this today. Just to finish with the 5,2 plus 2 cycloaddition, I forget these 2 slides, sorry. We try to understand why our reaction is totally regio and diastero selective. And so we did some calculation with theoretical colleagues. And as you can see, the observed product, which is this one, this is the product 8, is both the kinetic product and also the thermodynamic product. And at the last, we try to do this 5,2 cycloaddition reaction in enantioselective fashion, but unfortunately, whatever the nature of the chiral complex, so this is always a rhodium complex with a chiral ligand. In the intermolecular fashion, we never observe any enantioselectivity. So the yield has moderate to good, but we never observe any transfer of enantioselectivities. And we observe 5%, which is a very, very low EE in the intramolecular fashion. So we did not pursue our investigation with enantioselective cycloaddition. So now I switch to the talk of today. So we worked with the synthesis of gamma alkylidene butynolide. We did some post-functionalization of this gamma alkylidene butynolide. And we next turn attention to the ASA version of this gamma alkylidene butynolide, which are the gamma alkylidene butyrolactam. And these gamma alkylidene butyrolactam are interesting targets because you can find them in numerous natural products with a very interesting properties. So here I give you the example of pushinolactam, we talk about after. And this gamma alkylidene butyrolactam could be obtained from this gamma hydroxy butyrolactam by a dehydration reaction. And also these scaffolds are very interesting because, as I said, we can find them in several biologically active compounds or natural products also. The best way actually to access to this gamma hydroxy butyrolactam, not only the best way, but the method the most used, is to do a nucleophilic addition of a primary amine onto this gamma alkylidene butynolide. Okay, so this is a reaction which was already reported in the literature. So in our case, we wonder if it was possible to use our precedent methodology, our palladium-free Stone-Garchera coupling, to access this gamma hydroxy butyrolactam by adding at the beginning of the process a primary amine. So in fact, we want to use a multi-component coupling reaction, or copper-catalyzed multi-component coupling reaction between a terminal alkyne, a primary amine, and also an halogenated acrylic acid. So to make a very long story short, so we try to optimize this reaction, And we are very pleased to find that by using one equivalent of this iodo-butyric acid, two equivalent of terminal alkyne and two equivalent of primary amine, in presence of 20 mol% of copper 1, which is a copper iodide, two equivalent of base, mineral base, potassium carbonate, in isopropanol at 50 degrees, we're able to realize this reaction, including an enic-looping, an heterocyclization reaction, and the hydroxylase time formation, to give the corresponding with the desired product in a very good yield of 84%. And in this reaction, we are able to create in a one-pot fashion, one CC bond, one CO bond, and also two CN bonds. Now, all this reaction, the optimization reaction and also the stereoscope have been made on 2 millimole scale. And it's also interesting to note that this reaction could be done, could be scalable to 20 mol%, 20 mol scale to give so the same product with the same yield of 84%, and it will represent around 4.5 grams of a product in one step. So for the mechanism of this reaction, this is the mechanism we postulated. So the first step will be the oxidative addition of the copper 1 onto the carbon iodine bond of this carboxylate obtained by the presence of this base. After, we have the coordination of the triple bond to the copper to give this intermediate C. The next step will be the exchange of the ligand between the iodine and the acetylene thanks to the presence of the base. After, we will have the reductive elimination to give the enine moiety, in which the triple bond is activated by the copper. And in this case, we can observe the 5 exodig heteroxylation to give the corresponding vinyl cuprate. The next step would be the proto-determination of this vinyl cuprate to give the gamma-alkylidene butyronide. And when this gamma-alkylidene butyronide is formed, we can have the nucleophilic addition of the primary amine onto this carbon atom to give the corresponding amide, and the nitrogen atom could do another nucleophilic addition to give at the end the gamma hydroxy butyrolactam. So we next study the scope of this reaction. This reaction is very general. This reaction works very well since we're able to do more than 60 examples of compound. All our work as described in this paper in 2002, in which we have all the possibility to have the gamma hydroxy butyrolactam. So as you can say, as you can see, we can work with different activated terminal alkyne, such as aromatic alkyne, substituted aromatic alkyne, heteroaromatic alkyne. We can work with an ester, with a kettle function, and also with protected alcohol, benzyl alcohol, or TBS alcohol. We can also work with non-activated alkyne. In this case, the yield is lower than the other terminal alkyne, because in this reaction we can have the formation of this 6-member ring lactone, which is totally unreactive towards primary amine. We can also work with different primary amine. So what is very important in this reaction is to work with the nucleophilic primary amine. So we can work with propylamine. We can work also with this amino alcohol, and you can see that this reaction is totally chemoselective, since only the nitrogen atom could react. We can also work with this homoallele primary amine. We can work with less nucleophilic amine, such as vinyl or benzyl amine. But in these cases, if you want to have a good yield, we have to work with 3 equivalent of this primary amine. And the limitation of the reaction is reached with non-nucleophilic amine, such as aniline or aniline derivative, whatever the number of equivalent of this primary amine. We work also with different amine. We can work with ammonia, the simple primary amine. The yield are lower than the other, but in one step, we're able to obtain this gamma hydroxybutyrolactam without substituent onto the nitrogen atom, and this scaffold. I don't have an example here in my slide. We can find also this scaffold in several natural products. We can work also with this methoxyprimary amine, in which we can see the beneficial alpha effect of this oxygen atom. We are able to obtain this gamma hydroxybutyrolactam with a better yield than the analog without the methoxy substituent. Another thing very interesting is to work with a primary amine bearing an alkene, an alkene function. This is interesting for 2 things. The first one is that we're able to demonstrate that the triple bond of the activated alkyne react first in the Sonnegar-Chirac coupling compared to the alkyne function of the primary amine. So this reaction is totally chemo-G selective. And with such compound, we can imagine to do some another post-conjugation, such as the click chemistry, to have, for example, biological hybrid compound. And after we study the influence of the steric effect of the primary amine, and as you can see, with sterically under the primary amine, the yield drop from, for example, 75% to 25%. And this reaction works also with cyclopropyl primary amine, an interesting Banik block. Okay, we can also do a variation of the substituent onto the acrylic acid. We can work with more longer alkyl chains, such as butene, with methoxy methyl substituent, with a phenyl compound. Also, if you want to work with that substituent at the beta solution, in this case, the isolated yield of the product is very low, since we have the observation, we can observe the formation of the product arising from the 1,4 addition of the primary amine. Okay, so to avoid this reactivity, this 1,4 nucleophilic addition of gamma-amine, we synthesize, we think about a strategy in which we were able to use a TMS, temporarily protecting group of this double bond. So this gamma hydroxybutyrolactam could be obtained in moderate yield, and after we can desilylate this gamma hydroxybutyrolactam with sodium fluoride to give the corresponding unsubstituted gamma hydroxybutyrolactam. So we're not able to do this reaction in one step, but we can do this reaction in 2 steps by using this TMS protecting group. And to finish, we are also able to mix both of these different partners to give voilà, a large library of gamma hydroxybutyrolactam. We next also interesting to synthesize some biorelevant compound containing an indole moiety, which is a moiety which is well recognized in biological active compound. So we try to synthesize some gamma hydroxybutyrolactam indole hybrid scaffold, and for this we have two solutions. The first one is to incorporate the indole nucleus onto the primary amine. So we can start this reaction with a tryptamine, or we can also incorporate the indole moiety onto the terminal alkyne. So we can start our reaction with propargyl indole moiety, or with a terminal alkyne at the C3 position of the indole. And so starting from tryptamine or from propargyl indole, we are able to obtain on this biorelevant hybrid hydroxylactam and indole scaffold. Starting from this terminal alkyne at the C3 position, the yield is lower because we work with a non-activated alkyne. And as I said previously, in this reaction, we can observe the formation of the 6-member ring lepton. And as you can see, we can also work with different substituents and different terminal alkyne. So we next also turn our attention to the formation of this alpha halogenated hydroxylactam in order to alpha post-functionalize this lactam thanks to a palladium cross-coupling. So one more time, this reaction, as you can see, works well, but to have this yield, we have to work with this reaction with 40 mol% of copper instead of 20 mol% with the previous example. Okay, so as you can see, we can work with different terminal alkyne, with different primary amine, with different halogen atom, and we have also shown that we're able to do a Suzuki coupling reaction of this gamma hydroxybutyrolactam to give the corresponding alpha post-functionalized hydroxybutyrolactam. Okay, so after to have demonstrated the very potential of our methodology to access gamma hydroxylactam, we next okay, how many time I have to finish?
7 minutes, sir.
Okay, I'm sorry, I'm quite so we are interested in the post-functionalization of this gamma hydroxybutyrolactam. thanks to the reactivity of the corresponding acyl iminium, which can be related by an acid source. And from this acyl iminium, we can have two kinds of reactivity, which are the beta elimination to give the corresponding actinium butyroatom in absence of a nucleophile. And if you have a nucleophile in the reaction, we can have the nucleophilic addition of this nucleophile onto this electrophilic carbon to give the corresponding gamma fructinase lactam. And our strategy was to use a one-pot procedure, including these three steps: the formation of the gamma hydroxybutyrolactam, the formation of the acid iminium, and the post-fructinization. And the post-fructinization could be, as I said, the beta elimination reaction. And in our case, for the in presence of a nucleophile, we tried two strategies. The first one is when the nucleophile is onto the primary amine in order to access this fused polycyclic compound, or when the nucleophile is on the terminal alkyne to give the corresponding spirocyclic lactam, our very favorite compound. So we start with the synthesis of gamma alkylidene butyrolactam. So we did the same reaction. Okay, the only difference is the quench of the reaction. That means that by quenching the reaction with a solution of hydrochloric acid, instead saturated ammonium chloride solution, we are able to obtain the corresponding acyl iminium, and in absence of a nucleophile, we can observe the beta elimination reaction to give the corresponding alkylidene butyrolactam. So we did several examples. As you can see, this gamma alkylidene butyrolactam are obtained in a go yield. The J0 selectivity is not a total. We always observe the two J0-isomers. However, this is the Z configuration of this double bond, which is mainly observed. We can do also this reaction with alpha halogenated acrylic acid. And we are able to obtain this compound starting from TMS acetylene. So the yield is not very good. It's around 25% of isolated yield, which corresponds to 54% based on the starting the recovery of starting material. So the yield is not very good, but actually it's very competitive strategy, one-pot competitive strategy, to compare those which are described in the literature, which needs 5 or 6 steps to access this compound. So we next turn our attention to the polyheterocyclic lactam. In this case, we have a nucleophile present in the reaction. And for the first example, the nucleophile is bearing by the primary amine. And as previously, by quenching the reaction with HCl, we are able to observe the nucleophilic addition of the nucleophilic nucleus to this electrophilic carbon to give the fused polycyclic lactam. So we work with the tryptamine, and in this case, we are able to obtain the beta tetracarboline scaffold fused with a lactam moiety with a good yield. We can do also some phenyl craft reaction with an alren derivative, dimethoxyalren. And we can also work with this 1,3-aminopropanol to give the corresponding hemiaminal. And as we can see, this reaction is also chemoselective for the first step in which this is only the gamma hydroxybutyrolactam we observe. We did also this reaction with the nucleophile onto the terminal alkyne. And as I said, we are able to obtain the corresponding spirolactam moiety. Also, this reaction is works with acceptable yield, but it's not wonderful. Why? Because as I said, since we work with non-activated terminal alkyne, we can observe up to 0.5 or a majority the 6-member lactam. But for these cases here, we obtain the spiro 5-6 lactam in a very acceptable yield. So with this methodology, so we try to do the synthesis of a natural product. We are interested in Puschella lactam, which is a CD45 botulinum tyrosine phosphate inhibitor. Actually, there is 8 reports of the total synthesis of this natural product, with the yield ranging from 4 to 64% with different steps. And in our case, we're able to obtain this natural product in only 2 steps, with 30% yield of isolated yield. And to be brief, the first step is the use of our methodology. So we obtain this gamma hydroxybutyrolactam in moderate yield because we observe the formation of this 6-member ring. And after the next step is the deshydration reaction to give the exocyclic double bond, and at the same time the deprotection of the nitrogen atom. So we obtain this separable mixture of 2 diastereoisomers, the Z and E diastereoisomer, and at the end we are able to isolate the natural product in 71% yield.
I'm sorry, Professor, 40 minutes has passed.
Okay, so I finish. Just to say that now we are working in enantioselective intermolecular post-functionalization. And for this, we use the asymmetric counter-redirecting catalysis developed by List in 2006, and in which we have the Nobel Prize this year. So I won't give I won't talk about our work, but what I can say is that we have a very promising results, and I hope we will be able to share this results with you in the near few days. So as such to the conclusion, so I would like to thank all the students who work on this project. Dr. Fabien Rodier, which have done the 5+2 cyclo addition, and also this guy. I know you. I think you know these guys, which is Idham, who have done all the work on this. The synthesis of gamma hydroxybutyrolactam, and also the one post-functionalization and the total synthesis of the natural product. So thank you very much, Idham, for all the work we did in France doing your PhD. And I'll also to thank my collaborator, Dr. Jean-Luc Parrain, Gaël Chouraki, and also my theoretical colleagues for the calculation, and all this instance for the financial support, and you for your kind attention. Thank you very much.
Thank you for the amazing lectures, Professor. It is very interesting and mind-opening. And now let's begin the discussion session. To the participant who attend via Zoom meeting, you may ask your question via chat box or ask directly by enabling your mic or raise hand features. For participants who watch the live stream via YouTube, you may ask your question through the comment section instead.
Professor Laurent, can I ask you a question?
Yes, you're welcome.
All right. My name is Bimal.
Nice to
I
meet
am
you.
very curious to know, you have shown some IC50 data of some molecules, and which was 25, more than 25, even 124 micromolar. May I know whether you consider these molecules active against HIV?
Sorry, I didn't understand your question. So I shown. Can you repeat your question, please? No, you don't want? I'm sorry, but I didn't understand your question.
Okay, can I repeat it?
Yeah, sure.
Do you consider a molecule active against HIV if the IC50 data is more than 20 micromolar?
Yes, this is from reporting results. So yes, this is which one? It was for the microundulatancy. You are talking about this microundulatancy, for example.
You have one or two slides in which you have shown IC50 24 micromolar and 125 micromolar and 124 micromolar against HIV. Okay, if you do not get it, just leave it, please. I'll talk to you later. Thank you.
Okay.
Okay. Thank you very much for your wonderful compounds.
Okay, thank you.
Thank you very much for Professor Banik question. So is there any other question from other participant?
Perhaps from me.
Yes.
Okay, thank you, Professor Kamaras, for your presentation. So I have one question for you. So for the reaction 5+2 cycloaddition, is there any reason why did you use tertiary methyl ester in your starting material?
Okay, just I will share my screen. To be honest, because the synthesis of such diazo compound has been well described with tertiary terbutyl alcohol, and also because the intermediate of this reaction is ketene, and and the trap of the ketene with terbusanol is better than with methanol or ethanol, for example. Okay, it's just to have a better results at the end for the preparation of this 1,3 dipole. There is no influence onto the reactivity after for the cycloaddition. Okay, we have shown, we have seen that if you work with less nucleophilic alcohol, but less hindered, the formation of the ester is not as good as better than by the use of terbutyl alcohol.
Okay, Dr. Idham, is the answer from Professor Commeiras answer your question?
Yes, thank you.
Is there any other question for Professor Commeiras? If not, Thank you, Professor. That is the last question for Professor Commeiras that officially end the first lectures. And once again, thank you, Professor, for the information and knowledge that you have shared with us today.
Okay,
thank you. Our next lecture will be delivered by Professor Bimal Krishna Banik from Prince Mohammad bin Fahd University, Saudi Arabia. Allow me to introduce Prof. Banik. Prof. Banik received his PhD in synthetic chemistry from Jadavpur University in Calcutta, India. He is Fellow of Royal Society of Chemistry and Chartered Chemist of the Royal Society of Chemistry, United Kingdom, and a Fellow of the Indian Chemical Society. Professor Banik was a tenured full professor and first President Endowed Professor at University of Texas Pan American. And he was also the Vice President of Research and Education Development of the Community Health System of South Texas. At present, he is a full professor at Prince Mohammed bin Fahd University, Kingdom of Saudi Arabia. He has published 509 scientific papers and expecting to have more than 520 papers published by 2021. He experienced in developing inorganic catalysts, organic synthesis, metal-mediated reaction, green chemistry toward medicinal important compounds, investigated and analyzed in vitro, in vivo tests of many molecules. He is an active editorial member and reviewer in several international journals. He has numerous honors and awards that I cannot mention one by one, but the most recent was on 2020, he was selected as top 2% scientist in the world. What an amazing accomplishment our second guest lecture has. It is an honor for all of us to be able to be here and learn from Professor Banik about unprecedented reaction in water, synthesis of biologically active compound. Without further ado, let us give a warm welcome for Professor Banik.
Thank you. Let me try to share the screen.
Okay, Professor. For the next 40 minutes, the time is yours, and I'll be sending the reminder via chat box after 30 minutes has passed and 10 minutes are left. You may share your screen, sir. Thank you.
I cannot share the screen. It's not coming. Can you upload my presentation?
Okay, sir. I will share your.
Yes, it is going away.
Okay.
Good.
Wait a minute, sir.
Okay.
Let me set it to the full screen mode. Can you see it, sir?
Yes.
Okay.
Okay. Can I start now, sir?
Yes, you can.
Thank you. Today, thank you, everybody, all the participant, organizing committee members, ladies and gentlemen. I'll talk about bismuth nitrate mediated synthesis of molecules of medicinal interest. Most of the work was conducted at my USA laboratory, where I was a tenured full professor and president endowed professor at the University of Texas for 30 years. Next. Bismuth nitrate is an inorganic molecule and salt. We found from our study that bismuth nitrate is so versatile that it can give different types of products of medicinal interest. For example, it can be used for the synthesis of beta-lactam in chiral and achiral form. We can mix different types of steroid, heterocyclic compound, and many other reactions. I'll go one by one. Next. Bismuth nitrate is very cheap. It has acidic properties like Lewis acid properties because it has a vacant d orbital. It has also Bronsted acid characteristics. It is soluble in water and a very high coordinating power because of the vacant d orbital. The reaction codes can be manipulated. This has very high catalytic power and it can be used under different conditions without any problems. In fact, 100 milligram bismuth nitrate can be used for the preparation of 100-gram molecules. Here, I am showing first synthesis of keto beta-lactam here, following a known method. Next. Now, look the powerful nature of bismuth nitrate. Using keto beta-lactam and hydroxyproline, in one step, we prepared optically active pyrrole substituted beta-lactams. Synthesis of pyrrole substituted beta-lactam is not known. One may feel this reaction is very easy. Yes, reaction is easy now, but reaction was not easy up to 2014. This is the first report of synthesizing chiral pyrrole substituted beta-lactam, and this has been done by bismuth nitrate. This reaction produced two isomers. However, cis isomer was the predominant product. Using the chemistry of lactam, I have published more than 100 papers in one field, several patents, 3 books, and many other things you can check. Next one. Now the mechanism of bismuth nitrate catalyzed process goes through a protection of the keto group with hydroxyproline. The amino acid present in hydroxyproline reacted with the keto group in presence of bismuth nitrate and form a cyclic intermediate. This cyclic intermediate follows a unique pathway because this carbon 4 lactam hydrogen and the group selects the pathway or attack of the hydroxyproline from one side. After elimination and fragmentation, pyrrole substituted lactams are formed. If we do not have this hydroxy group, synthesis of the pyrrole will not be possible because to get aromatic character, we need to have this hydroxy. Next. Now, using this method of bismuth nitrate addition reaction, we have performed a number of bismuth nitrate catalyzed process. You see that here. And now, no, go back, sir. Yes, this one. Go back. Next. Yes. Reaction of hydroxy beta-lactam with glucose derivative. This is the glucose. Glucose can react with hydroxylactam and add the glucose unit to sugar. Next. Now this, yes. Now go back, sir. Yes. So here we have a different sugar molecules. We exploited the sugar chemistry using bismuth nitrate as the catalyst. What we have done, we have reacted diverse lactam, hydroxylactam with diverse sugar and demonstrated the effects of sugar and the stereochemistry of the lactam. Most importantly, we can add sugar to beta-lactam. Next. Here, I am showing the examples of different sugar unit and addition of different sugar units to hydroxylactam by bismuth nitrate. Next. Then after the addition of the sugar, it is possible to remove the sugar unit by bismuth nitrate also. That means bismuth nitrate catalyzed process is reversible process. One way bismuth nitrate helps to form the sugar containing molecule. At the same time, a prolonged exposure of the reaction mixture can destroy the sugar bond with lactam. The original hydroxy compound can be regenerated. Deglycosylation means removal of sugar can also be achieved by bismuth nitrate. Next. Here I am showing the amine addition. Earlier was hydroxy addition, and here amino beta-lactam can be added to epoxide sugar, and this can give optically active amino beta-lactams through stereospecific pathway. So earlier, the reaction was taking place with a hydroxy and unsaturated bond. Here, reaction is taking place between amino and epoxide in presence of bismuth nitrate. Next. Here, the mechanism of bismuth nitrate catalyzed reaction with sugar takes place through the participation of the anomeric oxygen. Anomeric oxygen present in 6-member sugar unit. 16 glucose derivative exist, and the glucose and the sugar oxygen atom acts and departs, forms a carbonium ion, oxonium ion. Then this oxonium ion helps to form the anomeric linkage between hydroxylactam and the sugar. And this helps to change the location of the double bond present in the sugar molecule to the next location. Originally, it was in 1,2 unsaturated sugar. Now it became 2,3 unsaturated sugar. This is possible because of the lone pair presence in the sugar units. Next one. Now you see some sugar unit cannot react with the same molecule even in presence of bismuth nitrate, because this sugar unit does not have the proper orientation or the right kind of living group. For example, in benzyl is not a good living group compared to acetoxy. That's why the benzyl protected sugar cannot react. Similarly, although we have acetoxy group present in this sugar, but the stereochemistry of the carbon 4 center prevents departure of the double bond. Therefore, no reaction has taken place even in presence of bismuth nitrate. So it depends on what kind of sugar we are taking. It also depends on what are the protective group present in the molecule. Next, sir. Now, using bismuth nitrate, we can nitrate aromatic hydrocarbon. Aromatic hydrocarbon can be nitrated using nitric acid, but the drastic condition is required. Bismuth nitrate can be used to nitrate diverse aromatic hydrocarbon in excellent yield. And I will show you why we are interested in nitrating polyaromatic hydrocarbon. Next. Here, nitration was also carried out with estradiol and estrone, which are hormone. The reaction of bismuth nitrate with estrone and estradiol accomplished the nitro derivative. The nitro derivative was required to functionalize estrone and estradiol. Without nitro group in the ortho position, no reaction can take place at the phenolic OH. Since no reaction can take place at the phenolic OH, because of the low acidity, addition of the nitro group was required. Next. Now, using the nitroestradiol, we alkylated the phenolic OH group. These are, the R means this kind of group. Now we have alkylated estradiol, and this alkylated estradiol can really inhibit breast cancer cell in vitro and also in animal model. So the purpose of using nitroestradiol is to do alkylation, and the alkylated product has shown activity against human breast cancer cell. So next one. Yes, this is the data of breast cancer cell against nitro derivative. After 72 hours, you see the cell viability is not there. That means all the breast cancer cell died. And this is the DMSO, the solvent. Solvent remains intact, no change of the solvent. But look, these 10 days, the molecules, our molecule affected, killed all breast cancer cell. 95% cell, breast cancer cell was inhibited. And this was possible by the addition of the nitro group ortho to the position of estrone and estradiol. Next. Now we are showing another important molecule that was used for beta-lactam synthesis. Next. Next. I'm skipping some because I have to maintain your time. Next. PBS one. Next. Okay, hold on. Ovarian cancer, please go back one. Yes, ovarian cancer is a very deadly cancer. It affects 1 woman out of 4 in the world, and the cases are increasing. And we have seen the stage and also the observed cancer patient and diagnosed cancer patient. It is a very serious disease. Some of the lactams that we prepared through nitration and reduction method have appreciable activity against ovarian cancer. Next. Here, beta-lactam, what I have shown you before, hydroxy, from hydroxy to acetoxy, that compound, when we have tested against ovarian carcinoma, what we find, the name of the carcinoma is SKOV. Ovarian cancer can be of different type. SKOV is the most notorious, very bad. Another one, OPCAR3. We have tested this molecule against the lactam that we produced, and we find within 7 weeks, we could stop the production of ovarian cancer in female. This was a remarkable study. As a result of this study, I was awarded several $1 million grant from United States. Next one. Now, these molecules can also be used against colon cancer. And you see, this is the not colon picture, and these are the stage 1, no sign. And you see that when you go to the stage 1, very little, we don't see even. Stage 2, we see little, and stage 3, as the stage goes up, we give bigger and bigger tumor, and the cure becomes more and more difficult. Next. The colon cancer similarly depends on the stages, and survival rate also depends on the stages. Next. Here, the molecule colon cancer, our one molecule acetoxy beta-lactam that we prepared through bismuth nitrate mediated method against HT29 became highly successful. Most importantly, the the well-known drug cisplatin erythromycins can also be effective against colon cancer, and people are using it, but they are highly toxic in nature. After 2 to 4 weeks treatment, patient cannot tolerate cisplatin and erythromycin. At that time, they get heart attack, because cisplatin and erythromycin can also generate free radical in the body. Therefore, patient can die not because of cancer, because of heart failure. And our molecules are not that toxic compared to cisplatin and erythromycin. Therefore, we have been given patent from United States and also from world. Next one, sir. Okay. Importantly, the lead molecules are not DNA intercalator. They are not topoisomerase inhibitors. Cancer drugs generally act against topoisomerase enzyme, but our molecule, we find they are not inhibitor of topoisomerase. However, they induce apoptosis in several types of cancer cells. I was showing you only 2 examples, but 64 cancer cell line exist. And we found very strange thing. This molecule upregulate the specific gene present in human ovary and the reproductive organ. Because of time limitation, I cannot go to discuss that part. Next, sir. Now I'll show you how the bismuth nitrate can be used to make complex molecule and keeping lactam unit intact through cycloaddition. The previous lecture was also given based on the cycloaddition, but our cycloaddition reaction is totally different than the previous lecture. Next one, sir. Here, the lactam, the diol lactam was prepared following known method. Next. Now you see, no, next. Okay, see here, this alkyne triple bond acetylene compound was added to the lactam. Then the ketal group was deprotected. Now I'll show you the magic. Next. Here, this diol and the alkyne connected to the beta lactam with different carbon middle chain. Tosylation of the primary hydroxy is possible in presence of secondary. And this secondary hydroxy then create an epoxide. And this epoxide on the treatment of sodium azide afforded a fantastic molecule. Next, sir. They afforded as this is the hydroxy, tosyl gone, azide came, and this azide underwent cyclization in presence of bismuth nitrate, and that forms a unique 3 tricyclic beta lactam, which has 1, 2, 3, 4 nitrogen, definite absolute stereochemistry connected to lactam ring. Synthesis of lactam with diverse ring system is a very important objective, perhaps one of the strongest objective present heterocycle. 86,000 publications are appeared on lactam units. So you can understand the intensity of beta lactam research, because this has number of application not only as antibiotics, because 86% antibiotics in the world belong to beta lactam group. Next. Now you see the higher member, instead of using lower member ring, now using the same chemistry in presence of bismuth nitrate, we have 4 and 8 member ring within the azide and alkyl cyclization can take place using lactam bismuth nitrate. A novel structure which are totally unknown in the world can be generated. using a simple reaction, using known method, and then using the knowledge of bismuth nitrate catalyzed cycloaddition. Next. 9-membered ring. So we have shown 7, 8, and 9. Synthesis of many distinguished scientists in the world claimed that synthesis of higher member ring fused to beta-lactam ring is not possible because of ring strain. However, our study indicates, yes, it is possible, and we have done it. Next. 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 Yes, hold on. So here, no, go back, sir. One time go back, please. Now we are showing how 2 beta-lactam rings are used with appropriate stereochemistry, and I will show you how this molecule can be used to create a novel structure using a single step in a symmetric way. Next. Yes, here look, 2 lactam units, and these 2 lactam unit by hydrogenation using bismuth nitrate, first reaction, deprotection, then oxidation, then Wittig reaction, create the substrate, and then do hydrogenation. That will give you a unique molecule that has 8-member ring in between, and 2 beta-lactams are fused to each other. Next. Next. Bismuth nitrate can also be used for Diels-Alder cyclization. Unsaturated compound, 3-component reaction with carbonyl compound and amine can be used to prepare heterocycles. In excellent yield, bismuth nitrate can be used as a catalyst. Next. Bismuth nitrate can also be used to synthesize dihydropyridine by Biginelli reaction. Next. Next. Dihydropyridine can also be used by bismuth nitrate catalyzed reaction. Very simple chemistry, but we can do the same thing using 5 mole% bismuth nitrate. This synthesis of dihydropyridine can be done. Next. Now, quinazoline, different types of quinazoline can be also be prepared. Unique quinazoline, this kind of quinazoline was not prepared before. This kind of quinazoline was prepared before, but here also we see 5% bismuth nitrate can induce this kind of molecule. Next. Here we see the biological activity of that particular quinazoline against skin cancer. And we see the molecule that using this, our molecule, we find the molecules are very active against skin cancer. Many people in the world ignore skin cancer, but they don't know that skin cancer can be very dangerous too, because when we see skin cancer, at that time cancer has started in other organ. Many patients, because we don't care skin that much compared to other organ. Next. See at the data here, human cancer, this is the molecule. You see how the cancer has been reduced here, the percentage with very little compound, how cancer can be inhibited. This is the control. This control agent does not inhibit that much. The molecule, our molecule inhibits more. Next. Next. Many pyrrole substituted molecules can be prepared following bismuth nitrate catalyzed Michael reaction. This paper was published in Journal of Organic Chemistry, American Chemical Society, and cited as the second highest cited paper, 517 citation. Next. Here, a very important reaction. This is the curcumin present in yellow spice. And curcumin was oxidized by bismuth nitrate to vanillin. Curcumin was oxidized to vanillin, a single molecule. From spice, we prepared the fruits. Next. 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 Here, I am showing that bismuth nitrate can also be used for the deprotection of the phthalimide, and then the amino group can be generated. Next. Here, very important reaction, the amino beta-lactam, which I have shown you before, can react with this furan derivative in presence of bismuth nitrate, and that can give pyrrole substituted lactam. The earlier I have shown pyrrole substituted lactam by reaction with ketolactam. Different chemistry. Here, reaction of the amino group with a unstable furan derivative gave pyrrole substituted lactam using bismuth nitrate. Next. Here, the mechanism, the process in presence of bismuth nitrate, the unstable furan undergoes deprotection, and that created an aldehyde. This aldehyde, on reaction with the amino group, created the pyrrole substituted lactam. Next. Here, showing a spirolactam can also be prepared because of the cycloaddition reaction, and unique pyrrole substituted lactams can be prepared. Next. Other molecules also. Next one. Next. Here, the last part of the method is very important for many purposes. Indole substituted molecules are very important because they can inhibit protein kinase C. Protein kinase C, tyrosine kinase C are the main target by chemists from biological medicinal perspective. And we have prepared a number of important indole substituted compound from beta-lactam using a concept which is not known. Next. Here, look at the beautiful part. Here we have indole and we have beta-lactam. Here we are using beta-lactam entire ring as an acid chloride equivalent, like acetyl chloride. CH3COCl. We are using the lactam ring, whole ring, substituted lactam ring, diverse ring as an acylating agent, and we reacted this acylated beta-lactam ring to react with the indole in presence of bismuth salt. Same thing, it is cis beta-lactam, this is trans beta-lactam. So cis and trans beta-lactam can be added to indole and can form an open chain ketoamine, because what happened, this lactam ring opens in presence of bismuth. I'll come back. In presence of bismuth salt, bismuth is acidic, vacant d orbital. It coordinates with the oxygen of the lactam. Thereby, when it coordinates with the bismuth, this carbon becomes highly nucleophilic. Then it attacks the most electron-rich center, the way we have done Michael reaction. So using Michael type of concept, the indole 3 ring activated. This 3 activated ring attacks the less highly positive carbonyl group of the lactam, and this carbonyl itself is a positive, but it becomes more positive due to the activation of with bismuth, because then it opens. Next one. Like this, here bismuth coordinates, that creates much more positive lactam unit, and that's why this 3 position reacts here, that opens up the lactam ring. Next. Now bismuth, this opens CO, this CO, the Z, Y, NH2. Then after that, the standard chemistry hydrolyze this and cyclize with this amino, which is not a difficult process. Then if you rewrite this open chain molecule in this way instead of this way, and if you have ester group here, you can cyclize to the different side. So using the side chain containing molecule, you can form different types of ring system which are not known. So novel protein kinase C inhibitors using indole and beta-lactam can be achieved And this key point of this reaction is bismuth nitrate induced ring opening reaction of the lactam selectively, and then use that system to activate the indole 3 position. Then after that, routine chemistry and develop this molecule. Next. In conclusion, we have synthesized a number of beta-lactam in chiral form. We have demonstrated the activity of the beta-lactam against diverse cancer. We prepared steroid and we have shown some biological activity. We prepared a number of heterocycles, and using the method, we prepared number of useful organic molecules that was used for structure activity, and we have found novel structures for biological medicinal application. As a result of this study, our study was proved to be very important because not only I got a lot of benefits, award, I got more than 25 awards in international level, including award of Mahatma Gandhi Award from Queen Elizabeth. And I am very happy that this work was possible because of a number of workers. Please, next. Some of the workers who have 400 members work with me in my projects. So I recruited several people, and you can see a number of PhDs, names are here, who have contributed in this project. I am also very grateful to USA National NIH Drug Discovery Program, MD Anderson Cancer Center, because MD Anderson Cancer Center ranks #1 in the world in cancer research and treatment. And I was there for 11 years. I worked there for 11 years. And finally, I like to acknowledge next. Some undergraduate students who work with me, 17, 18-year-old, ultimately they became very successful, and I like to acknowledge them. You see all the students, undergraduate, 17, 18-year-old student work with me, and I think maybe more than 100 undergraduates work with me, and they have achieved very great success. Next. And this was, I told you before, that this work was supported extensively because of the novelty and because of the uniqueness by the top funding agency in the world, National Institute of Health, US, National Cancer Institute, private foundation, Kleberg Foundation. They provide only 2 grants per year, and many other universities. I am very grateful to them. Next. This thanks to two professors who invited me, one from Indonesia and one from France, to deliver this lecture. And I wish to thank all of you for your participation. I wish you all the best in your career and in your future. Thank you very much. I am very grateful to you. I'll be happy to answer your question.
Thank you, Professor Banik, for the amazing lectures. It is very interesting and mind-opening. And now we begin discussion session. To the participant who attend via Zoom meetings, you may ask your question via chat box or ask directly by enabling your mic or raise hand features. For participants who watch the live stream via YouTube, you may ask your question through the comment section.
I have a question.
Professor.
So thank you, Professor Banik, for your interesting presentation, especially for the cascade reaction. Yeah, interesting. You have. So I have several questions. First one, in here, you develop synthetic strategies by using bismuth nitrate as the catalyst, as the acid catalyst. Well, as we know, the commonly known acid catalyst is the triplet. For example, bismuth triplet and another metal triplet. So, do you have? Could you please give a comparison between your bismuth nitrate and also the the bismuth triplet, especially the performance in organic synthesis. And then the second one, probably you have the how do you say, you have shown us about
Sir, your voice is not coming well. Your voice is getting fabricated because some noise is coming.
okay, sorry. So I think that I will repeat the question. So you have developed the bismuth nitrate, yeah, synthesis of various organic structure.
Yes.
So as we know, for example, bismuth triflate, yeah, the triflate is commonly used acid catalyst. So could you please give a comparison between these two catalysts, acid catalysts, in connection?
Bismuth nitrate and what? And what?
Bismuth triflate.
Triplet. Okay, very good.
Okay.
Very good question. Actually, what you asked me, that is a very standard question. Many people ask me this question. Okay. Bismuth triplet is toxic, very toxic. If you take, when you do bismuth, reactivity of bismuth triplet is also high. But what we found, when you consider bismuth triplet as the Lewis acid, then bismuth nitrate is better than bismuth triplet. When you consider bismuth triplet as a bond-state acid, then bismuth triplet is better, mean acidity is higher. When you consider bismuth triplet as a bond-state acid. Yes. However, in our reaction, we have used the coordinating power of bismuth nitrate, not the acid-inducing power. Coordinating power of bismuth nitrate means Lewis acidic power was used. Therefore, okay, bismuth nitrate coordinates in a much better way than bismuth triplet. When you consider acid-releasing property, then bismuth triplet is equally active like bismuth nitrate. For example, when you perform the Diels-Alder reaction, what I have shown you, one-step reaction, in those reactions, bismuth triplet is equally active like bismuth nitrate. However, bismuth triplet is toxic and it takes much more amount than bismuth nitrate. We prefer bismuth nitrate because it is non-toxic, it is edible. You know, many countries, people take bismuth salt, bismuth nitrate, bismuth chloride to control the acidity of the stomach. We found bismuth nitrate, even 10% bismuth nitrate is not toxic. Whereas when you open bismuth triplet, you see the fumes come, lot of fumes come, and this is because of triplic acid. Triplic acid is poisonous. So, therefore, we wanted to use bismuth nitrate. Moreover, when I started this program many years ago, at the time, bismuth triplet was not there in the market. We use bismuth nitrate, bismuth chloride, bismuth subnitrate, bismuth sulfate, bismuth oxide. Then we found bismuth nitrate is the best catalyst because it gives you the product what you want to know. And another thing, bismuth triplet is a liquid and bismuth nitrate is a solid. To take the weight of 5 milligrams of bismuth nitrate is comparatively easy because it is like sugar crystals. It is crystal. And bismuth triplet is not, it is like a heavy dense, like honey powder, honey liquid. It is very difficult to take the weight. So if I ask a student to take 10 milligrams of bismuth salt, bismuth nitrate or bismuth triplet, the student get difficulty. Instead of using 10 milligrams, student may use 100 milligrams because one drop of bismuth triplet actually 100 milligrams. But I can measure 5 milligrams bismuth nitrate using a very small spatula, using 2 crystals from that solid bottle. And to weigh 5 milligrams honey is very difficult. Similarly, to weigh 5 milligrams bismuth triplet is very difficult even for me.
Okay, thank you. So it is the first time for me to know that the bismuth nitrate is edible. Thank you. And then the second one, so
okay, now there is a question of edible. Somebody takes any acidic compound large excess, that can create problem also.
Okay.
Yeah, something the medicine available in the market. I have seen the medicine available in the bismuth salt. In America, I see the medicine. I do not know. I know India also we have the medication. But again, when you people take excess medication without having the right symptom, that can create trouble. drug-drug interaction can take place. Many people in the world take unnecessary medicine.
Yeah. And the next question, yeah, you have developed the cyclic addition by using azide. Yeah.
Yes.
So you use the bismuth nitrate also as the catalyst. Yeah.
Yes.
Have you ever tried? But because normally we use the copper catalyst.
No, thermally, it is possible. In principle, it is possible.
Yeah.
Yeah, but we have not thermally, photochemically, it is possible.
Okay.
But we have not done thermally because the reason is very clear. The United States funding is very competitive funding. They don't like to hear the whatever other people have done. So I had to tell them, look, my method is the best method. I do not care other method. Yes, okay. Because the moment I write the other methods I have done, the people will say, hey, what's the big deal? Other people have done also.
Yeah.
Yes.
And the last question for me, yeah, you have also developed the oxidation of curcumin.
Yes.
Yes. Could you please show us about the mechanism?
The mechanism here, this is very interesting.
Yeah.
Because the reason I have taken a curcumin, because I thought I will get nitration of curcumin.
Yeah.
Because of the power, because of the Wedge activated group. But then when I took my student postdoc took the spectrum and he said, he came to me, sir, the action did not work. I said, what happened? Sir, so my spectra is different. This whole molecule, nothing I see. Then I say, oh my God, what happened? The middle part, curcumin is symmetrical molecule.
Yeah.
The middle part was degraded. That's why the spectra became very simple. What happened? We have demonstrated before that bismuth nitrate can also act as an oxidizing agent. I have maybe 25 papers on bismuth nitrate as oxidizing agent. So here, instead of acting as nitrating agent, oxidation of the enolic double bond was taken place. That's why this is simple oxidation, double oxidation, like permanganate. If you use potassium dichromate, same thing will happen. We have seen the potassium permanganate, potassium dichromate can give the same product.
Okay.
Even when I first started the bismuth nitrate, I was working on sodium bismuthate. Sodium bismuthate is like sodium permanganate, potassium permanganate, and potassium dichromate in terms of oxidation potential. 1.52, 1.48, 1.38. Then we found that sodium bismuthate can oxidize a number of organic molecules. Nobody used sodium bismuthate in organic synthesis, but inorganic chemists use sodium bismuthate. Then I started to oxidize benzylic methylene. And yeah, I got the product. I published in Tetrahedral Letter 1998. Then several other papers, I oxidized bacatine, the Taxol intermediate also. But anyway, curcumin was oxidized in the middle part of the molecule because of the conjugated enolic double bond. This is simple oxidation method, nothing more.
Okay, thank you very much, Professor.
Okay, thank you. Any other question?
Yeah. Thank you, Professor. Is there any other question from other participants? It looked like that your presentation already pretty clear, sir. So I think that is the last question for Professor Banik, and that officially ends the second lecture. Once again, thank you, Professor, for the information and knowledge that you have shared with us today.
Thank you.
Thank you, Professor.
Thank you.
Our next lecture will be delivered by Dr. Valeria Palermo from Universidad Nacional de La Plata, Argentina. Allow me to introduce Dr. Palermo. She completed her PhD on organic chemistry in 2012 at the National University of La Plata, Argentina. Since 2014, she has been a connected researcher at Syndeca. Her current research involves the design, preparation, and characterization of catalysts using bio-waste from citrus and their application in eco-friendly oxidation of sulfide and multi-component synthesis of heterocyclic with potential bioactivity. She published over 25 papers in peer-reviewed journals and counting. She has participated in 14 funded projects, being the principal researcher of one of them. In addition, she has acted as reviewer in scientific journals such as Current Organocatalyst, Applied Organometallic Chemistry, and Letter of Organic Chemistry. She is member of Teacher Selection Commission in Nacional University of La Plata since 2005, and also as external evaluator of PICT project from Argentina since 2020. It is an honor for all of us to be able to be here and learn from Dr. Valeria Palermo about green synthesis of heterocyclic compound using heteropolyacid as catalyst. Without further ado, let us give a warm welcome for Dr. Palermo.
Thank you for the presentation. Can you hear me?
Yeah, I can hear you, Professor.
Okay.
Hi, Doctor. Okay, Doctor, for the next 40 minutes, the time is yours, and I'll be sending the reminder via chat box after 30 minutes has passed, and 10 minutes are left. Thank you.
Okay, I started to share. So, well, yes, here is, well, sorry, my presentation is very slow, but I think in a few seconds.
As we can see that.
Okay. Then 1 minute. I want to, I can, oops. Sorry, I want one. Oops. Here. Well, first I want to say good morning and good afternoon to everyone. And I want to thank to the organizer of World Class Professor 2021, and especially Dr. Idham for the invitation. And the title of my talk is Green Synthesis of Heterocyclic Compounds using Heteropolyacid as Catalyst. I'm here in La Plata, in Argentina, and National University of La Plata is one of the most important Argentinian universities. It has 17 schools, more than 100 degrees, and 170 postgraduate courses, over 100,000 students, and many academic research centers. I study and now teach and work in a School of Exact Science, particularly in Sindeca is one of the research and development centers in applied science, in which more than 40 research work and 25 students are doing their PhD and postdoc. I belong to research group of Gustavo Romanelli and Patricia Vázquez, with Gabriel Satic, Diego Ruiz, Eliana Nope, María Belén Colombo Miglorero, and Angélica Escobar. Well, as its definition indicates, green chemistry efficiently uses raw materials, eliminates waste, and avoids the use of toxic and hazardous reagents and solvents in the manufacture of an application of chemical products. The principal objective is to design eco-friendly processes, taking into account the environmental impact of chemical and the process by which they are produced. Anastas and Werner developed 12 principles to make a process more environmentally friendly. And when a process is designed, these principles must be considered. And the challenge is to achieve with most of them. In our group, we focus on atom economy by the use of multi-component reaction, and in catalytic process using heteropolyacids. A catalytic process are preferred to avoid the use of a stoichiometric substrate and mineral acids, which require quenching and neutralization steps to remove it, and resulting in enormous quantities of waste. The catalysis can be homogeneous and heterogeneous. In homogeneous processes, usually are obtaining best yields and selectivity, but heterogeneous catalysts are preferred by their stability, easy recovery, the reduction and the reduction of waste generation. Heteropolyacid compounds are stable solids, which consist of a metal oxide cluster of early transition metals, such molybdenum or tungsten, with one heteroatom, like phosphorus or silicon, and they could be heteropolyacids or their size. And in the solid state, the hierarchical structure of the heteropolyanions are, in primary structure, is the structure of the molecular, and the secondary structure is the three-dimensional arrangement of the polyanions and countercations, and the tertiary structure is the assembly of the secondary structure into solid particles. And this structure determines the particle size, surface areas, and pore structure. There are many different kinds of heteropolyacid, which principally are used in catalysis. The most developed and famous heteropolyacid is the Keggin structure, with the general formula is this, in which consists on 12 octahedrons organized in triplets arranged around a central tetrahedron. On the other hand, Wells-Dawson structure consists of two identical trivacan lacunae Keggin special, these trivacan lacunae resulting from the loss of this octahedron, and they are linked through the oxygen atoms. And Preissler heteropolyanion consists of 5 units, identical units, deriving from the Keggin anion by the loss of 2 sets of octahedras, forming this Preissler heteropolyanion, forming a cyclic assembly. Heteropolyacid compounds are stable solids, possess a very strong acidity. They can be used in mild reaction conditions, are easy to handle, no corrosive, no explosive, produce good yields and selectivity, and the isolation of the product and the catalyst are simple, and resulting in a reduction of waste and by product generation. Especially heteropolyacid have a strong Bronsted acidity, redox properties, high proton mobility, and stability. And their use as solid catalyst is a green alternative to the liquid acid, such as traditional mineral acid, both in industrial and academic transformation. The acidity of the heteropolyacid approaching the superacid region and can be measured by potentiometric gradation. And the classification of these sites as Lewis or Bronsted can be made by infrared spectra of absorbed pyridine or temperature program absorption, desorption of ammonia. Phosphomolytic acid and phosphatoxic acid are commercially available, and the heteropolyacid resulting for the substitution of one molybdenum for another atom can be prepared by hydrothermal synthesis from an stoichiometric mixture of the respective oxides, and Wells-Dawson heteropolyacid can be prepared from the potassium salt, which are made from the sodium tungsten, and then the salt was treated with hydrochloric acid. On the other hand, Preissler heteropolyacid also can be prepared from the potassium sodium salt, prepared again from the sodium molybdate and tungsten, and then this salt was passed through an iron exchange resin. Heteropolyacid are used as catalysts in organic synthesis, such as heterocyclic preparation, protection and deprotection of functional group by means of esterification and esterification reaction. In these processes, the heteropolyacids act as acid catalysts, and also they can be act as redox catalysts in the oxidation of alcohol, phenols, amines, and sulfides. In this presentation, I present some examples of the use of heteropolyacid in the heterocyclic synthesis. One of the disadvantages of use bulk heteropolyacid in as heterogeneous catalyst is the very low surface area and the fact that it can be dissolved in various reaction media, especially in polar solvent, and the separation is very difficult. For this reason, many strategies to turn the bulk heteropolyacid into an heterogeneous catalyst was developed, such as solidification, which consists in the formation of an insoluble ionic salt, or immobilization on a support by different methods, such as impregnation, templating, grafting, or by modification of the surface of the support. The solidification can be done using metal or organic cations, and when the organic cation is very large, the resulting catalyst is called micellar, and they can be prepared from the aqueous solution of the heteropolyacid and the ammonium or pyridinium salt. For the mobilization and the support can be present stability, provide high dispersion of the heteropolyacid, and allow modify the surface. Among the most used support are silica, active carbon, alumina, titania, organic polymers, among others. In our lab, we prepare silica by Sol-Gel technique in a nitrogen atmosphere. We use this glove box. And for the impregnation of the support can be used equilibrium absorption technique or incipient wetness. Sometimes for improve the according of the heteropolyacid into the silica surface, the silica is functionalized with amine group for improve the interaction between these heteropolyacid and the silica surface, and this is for minimize the leaching of the heteropolyacid when are used as catalyst in one reaction. The incipient wetness consists in contacting the support with a solution of the heteropolyacid, and in this technique, the volume of the solution is equal to the pore volume of the support, and the heteropolyacid is introduced into the support pores by capillarity. And by equilibrium absorption technique, the impregnated solution is used in a huge volume, and excess of volume of this impregnating solution is used. And this system was shaken for many hours and then kept undisturbed. And finally, the remaining impregnated solution was removed to obtain the solid. In this technique, the diffusion process and the long time of contact between the support and the solution give a better distribution of the heteropolyacid into the support. Other interesting methodology to impregnate the support with heteropolyacid is the inclusion, in which the heteropolyacid is introduced into the silica matrix during the synthesis of the silica using Sol-Gel technique. Our research group has employed different heteropolyacid on many supports such as silica, alumina, zirconia, titania, etc. In this slide, I present some of the families of heterocyclics that can be prepared using heteropolyacid as catalysis, and many of them can be obtained using multi-component reaction, and their compounds, many of the compounds are important in pharmacological and agrochemical industries by their bioactive biological activity. Multi-component reaction is the reaction in which one product is built from 3 or more reactants in a single operation, and usually only one product is obtained, and it's considered a green process due to the high atom economy, which is defined as the molecular weight of the product divided the molecular weight of all the substance used. And a multi-component reaction has a low E factor, which is the mass of the waste generated divided the mass of the product. Using multi-component reaction is avoided the protection step, hardly workup, purification process, and aggressive reaction condition, and resulting in the reduction of chemical waste generation, the formation of secondary product, operation cost of time. And usually the workup is via precipitation of the product by addition of water. The first family is the dihydropyrimidinones. Many of them are reported as biological activity, and they can be prepared from Biginelli reaction. Is a cyclocondensation catalyzed by an acid. Many different acids was reported for this reaction, including heteropolyacid. When K heteropolyacid doped with vanadium and bismuth, we obtain very good yields under solvent-free conditions. And we observe that the incorporation of bismuth and vanadium into the primary extractor of the heteropolyanion improve the catalytic activity according to the acidity of the catalyst. And the product was isolated after additional of water. Many compounds using different aldehydes and urea or thiourea was obtained with very good to excellent yields and high selectivity. And for the reuse of the catalyst, the mixture was treated with hot toluene, and the catalyst remain insoluble, and they can be separated from the product. And we observe that the catalytic activity is maintained after 3 reaction times. With this protocol, monostrol can be obtained with excellent yields and is reported as the use in cancer therapy. Also, copper and iron was introduced in the secondary extractor of the heteropolyanion, and again was observed that the incorporation of the metal was in the secondary extractor or in the primary extractor, the vanadium in this case, improved the catalytic activity according to the increasement of the acidity of the heteropolyacid. 22 different compounds was obtained with very good to excellent yield, including monostrol and piperastrol. And the reuse of the catalyst showed that the activity is maintained after 3 rounds. And also, in order to quantify how much greener the methodology is, atom economy and process mass intensity was calculated. Process mass intensity is the ratio of the total mass used in the process divided the mass of the product. And the high atom economy and low process mass intensity indicate that this process is green. Also, West Dawson was tested as a catalyst using refloxing acetonitrile and solvent-free condition. Again, very good yields was obtained for the obtention of 15 different compounds. And K heteropolyacid impregnated in different support by equilibrium absorption technique was also used as catalyst in this reaction. And in this case, the support was prepared with different composition of waste, such as sand and cement from the building industry, non-returnable glass bottles, and used tires. With this catalyst, good yield was obtained, especially with impregnated sand catalyst, which present a higher acidity. And for the reuse, the reaction mixture was treated with hot toluene, and again, the catalytic activity is maintained after 3 reaction cycles. With this catalyst, we obtained 7 different compounds with good yield, including monastrol. Also, precyl erythropolyacid encapsulated in a silica framework prepared by inclusion technique was evaluated as catalyst. In this case, it was interesting that as aldehyde was used furfural and 5-hydroxymethylfurfural that could be obtained from biomass. And this catalyst was evaluated using solvent-free condition under conventional heating and microwave irradiation. In both cases, good yield was obtained, and the catalyst was separated by addition of acetone when the mixture was cold, and they can be reused again. With this protocol, we obtain a better result with conventional heating, but the reaction time need for the complete the reaction using microwave was shorter. And atom economy and process mass intensity show that the process are green. And an important family are the fluorine hexahydropyrimidines, which are important in the synthesis of therapeutic drugs. And the fluorine atom is similar in size with the hydrogen atom. So the replacement of fine hydrogen by fluorine is not expected to cause any significant change in the molecular geometry and shape, but the high electronegativity of fluorine has a strong effect on the electronic properties of the molecule. They can be obtained by a variation of Viginelli reaction employing ethyl 3-fluoroacetoacetate. For this synthesis, we use phosphomolybdic acid doped with vanadium in the primary structure, encapsulated in the silica framework prepared by inclusion technique. We prepare catalysts with different heteropolyacid load, and the reaction was done under solvent-free condition, and the catalyst can be recovered by addition of acetone, and the catalytic activity is maintaining after 4 runs. A very good yield was obtained for 11 examples. Also, precyl erythropolyacid, including in a silica matrix, was evaluated as catalyst. Again, very good yields was obtained. And the green metric for this reaction demonstrate that the process is green. Other family are dihydropyridines, which many of them are reported as therapeutic with therapeutic use, especially as calcium channel blockers. And symmetrical dihydropyridines can be obtained by Hans reactions. This is a condensation between aldehyde, ammonium acetate, and 2 equivalent of beta ketoester. And also asymmetrical dihydropyridines can be obtained for starting from 1 equivalent of beta ketoester, and then use one enamine prepared before. West-Dawson and precyl erythropolyacid was used in the reaction, and very good yield was observed. And when ammonium acetate is replaced by aniline, this family of compounds can be obtained. In this reaction, micellar Keggin heteropolyacid was employed, and we prepared 4 different micellar compounds using 2 different ammonium or pyridinium salt and these 2 heteropolyacid. In this case, the reaction was made in refluxing ethanol, and good result was obtained. And the catalyst can be separated by filtration because it's insoluble in the reaction media, and the catalytic activity is maintained after 5 reaction cycles. Also, we represent the radial pentagon for the synthesis of nifedipine. This pentagon, in this pentagon are represented 5 green metrics such as atom economy, reaction yield, the reciprocal of stoichiometric factor, material recovering parameter, and reaction mass efficiency. These values are between 0 and 1, and when all of them are 1, resulting in a regular pentagon, is the greenest situation for the reaction. And these pentagons are used to detect the most sensitive point in the reaction. And now can we see that the reaction mass efficiency must be improved to turn this reaction greener. When 3,4-milchromone was used as aldehyde for the preparation of the dihydropyridine, in an important presence of this product was obtained, and this product can be formed by the opening of this ring, and then a cyclodehydration occurs, and it's due to the high selectivity, high reactivity of the center. And in this table, it will show the selectivity toward the Bose product using the traditional condition for the obtention of the Hans reaction. And when only one equivalent of beta ketoester are used, the selectivity to the functionalized pyridine is improved. And the reuse of the catalyst show that the activity is maintaining after 3 reaction cycles. Other important family are the tetrahydropyridines. With this ring are present in many different natural products, and can be used as in food additives and in therapeutic application. And the activity depends on the nature of the substituent. These kind of tetrahydropyridines, densely functionalized, are reported to be antimicrobial, antioxidant, anti-cancer, among other bioactivity, and can be prepared from the pentacomponent reaction between 2 equivalent of aldehyde, 2 equivalent of amine, and 1 equivalent or a beta ketoester. And in this reaction, 5 sigma bonds and 2 stereogenic centers are formed. Kegging heteropolyacid was used in this reaction in methanol and room temperature, and long reaction time was needed to achieve the reaction, and the yield was low to good depending on the nature of the substituent. Now we are studying the use of the Kegging heteropolyacid encapsulated in a silica matrix containing orange peel, thermically treated, prepared by inclusion technique. And in this case, the reaction was made under solvent precondition, and for the workup is needed to the addition of an organic solvent such as dichloromethane to dissolve the product and separate the catalyst and reuse. Other important family of compounds and chromones and flavones, which are present in many natural products, especially and they can be found in different parts of the plants, and present different biological activity, and they can be obtained for starting from the dipropanone by acylation. It's not a multi-component reaction, but can be catalyzed by acid. And in this case, the reaction was made using glycerol as solvent. Glycerol is considered an environmental or green solvent because they can be obtained from biomass as a byproduct in the biodiesel production. And they allow to make the reaction at higher temperature. And the solubility of the heteropolyacid into the glycerol enables the easy separation of the product by addition of an organic solvent such as ethyl acetate. And this system's catalyst solvent can be reused, and the activity of this system was maintaining after at least 4 reaction cycles. And for this reaction, green metrics was calculated, and we found that the reaction is green processes, and especially material recovery parameters are 1 because the solvent and the catalyst can be reused, and water is the only byproduct. Other interesting family because their biological activity are 2-amino-3-cyanochromenes and xanthenes. And when the reaction to the obtention of this chromene were done using K heteropolyacid, an important amount of xanthene was observed. So to improve the selectivity to this compound, the reaction was start with use the intermediate formed between the aldehyde and malononitrile as a starting material. And again, with this, using this methodology, an important amount of xanthene was observed. And even when benzaldehyde wasn't used as a substrate. And this can be explained by the fact that the formation of these benzylidene malononitrile are irreversible compounds. So even started with this intermediate, benzaldehyde present in the reaction is present in the reaction media, and the xanthene is formed. When the catalyst is recovered and reused, the same conversion and selectivity to the both products are maintaining after 4 reaction cycles. Other important families of heterocycles that can be obtained from using heteropolyacid as heterocycles are quinolines or quinolones. Very good yields was obtained from the desired product. Also, tetrahydroisoquinolines and benzodiazepines were obtained using heteropolyacid as catalyst. And quinoxalines are other families of compounds that can be obtained with good yields using heteropolyacid. And benzodiazepines can be obtained in very good yields. Another family of compounds that was prepared using Kane or West Dawson heteropolyacid supported on silica or silica alumina, all of them with very good yields. As conclusion, it can be said that heteropolyacid efficiently act as heterogeneous catalyst, and different kinds of heterocycles are obtained, many of them by multi-component reaction, using heteropolyacid as acid catalyst. And mild reaction conditions are used, and in most of the case, good to excellent yields were achieved, and heteropolyacid catalyst can be easily recovered from the reaction media and reused without the loss of catalytic activity. Well, finally, I want to thank to Nacional University of La Plata and CONICET for the financial support. And again, thank you to the organizer of World Class Professor for the invitation, and thank you for the attention.
Thank you for the amazing lecture, Dr. Palermo. It is very clear, interesting, and mind-opening. Now we begin the discussion session. To the participant who attends via Zoom meetings, You may ask your question via chat box or ask directly by enabling your mic or raise hand features. For participants who watch the live stream via YouTube, you may ask your question through the comment section instead.
Professor Valeria, can I ask you a question?
Yes, of course.
I see you have done a lot of work on heterocyclic synthesis using this polyacid, and I am sure you have seen some of my compounds. I have performed this reaction using bismuth nitrate.
Maybe,
right?
yes.
Yeah, a few minutes ago, you have seen almost all these materials you have published, I also done. Okay. Now, I use different catalysts. Now, you have used microwave in one of your examples used. What kind of microwave you used in your reaction?
It's a lab microwave. Is I don't remember we can choose the potential and the temperature. It's not domestic microwave. It's a laboratory microwave, and we can set also the temperature and the power.
Okay. In this microwave, can you control the temperature?
Yes.
How?
There are a setting, and when set the temperature, the potents need to get this value, make a pulse of the potential of the power, and the temperature are maintained for the time that we selected.
Okay. You know that in science, a lot of debate is going on in the world whether microwave is assisting the reaction or microwave is helping to get the product because of overheating. Microwave has any effect or the temperature has the effect?
Yes, and sorry, I don't heard the question.
Okay, my question to you, whether you think that your reaction is accelerated because of microwave radiation or your reaction is accelerated because of microwave heating?
We found it, depending on the reaction, some of them can be activated from the temperature that can be get in short time, and in other case the reaction was worse in microwave. With microwave was used as power.
Okay. Okay. Now you have also used. You have shown that your acid has worked better when you use clay instead of silica. Clay was better than silica when you conducted some experiment. Am I correct?
Sorry, clear with what do you mean? What clear?
Clay with your acid was better active than your silica and acid.
Okay.
You have shown examples. So,
yes.
Okay, now can you tell me why? Can you tell me why?
In some reaction is because the amount of the heteropolyacid, which is the active phase, is bigger in when only heteropolyacid are used, and when it's supported on the silica, many times the proportion of active phase is lower, and many times the access to the substrate to the active site is not so efficient in when bulk heteropolyacid are used. But the separation process is much easier when it's used as supporting in or included in a support. So we supported by simplify the isolation, and in this way we can reuse again.
Do you know that the reactions you have performed with your acid, all these reactions, whatever you have demonstrated today, I know all these reactions can also be performed only with clay, without using any acid.
Which reaction?
All reactions. Whatever reaction you presented today.
Sorry,
all these reactions can be performed with clay, for example, bentonite and montmorillonite. People used montmorillonite and bentonite clay to make this product. Exact yield, I don't remember, but I have seen the paper, your dihydropyridine, all the methods you have shown, Biginelli, hands, reactions, people performed with clay only, microwave or no microwave. Here you are using one, that's the reason I want to know the advantages. You are using acid and clay. People performing clay is the best. So what are the advantages? I did not get your advantages of using clay and acid together. You understand?
In many times we study the use of the heteropolyacid because are a greener option in comparing with other catalyzed or solvent. So we study, we objective is to make a greener process. All of them are reported, and many catalysts and reaction medias are used, but our focus is into make this process more environmentally friendly. Sometimes we get, or sometimes the results are not expected, but this is our objective.
Okay. Yes. Valeria, you are giving me answer, and those answer actually I'm not looking for. I am looking for an answer, that is, I am trying to find out also whether this acid really binds to the surface of the solid, and what kind of reaction take place because of the acid, your acid, and the solid surfaces. Whether any different, because of their combination, whether any different types of acidic material generates that accelerate the reaction, or how this acid gets more powerful in presence of those solid. That is, I am trying to find out. You understand now?
I think
Yes.
when the heteropolyacid are included in a silica or in a support, many of the time the acidity is lower because of the interaction with the
this is the thing. If you can do it experimentally, if you can demonstrate some data how the acidity can be changed by adding acid to the different types of surfaces, that would be a good study for you. That would be a good study.
Yes, we in our publication, the acidity was one of the properties that we measure, and we use it in some time. In some reaction, the lower acidity of the support helping to the selectivity.
All right. Yes, that would be a good study to know, because many people then try to get the advantages of doing some chemical reaction following your methods and other methods. Thank you.
Thank you,
Valeria. Thank you.
Thank you, Professor Banik and Dr. Palermo for the discussion. Is there any other question from other participants?
Okay, for me.
Yeah.
Okay, thank you, Fale, for an interesting presentation. It is very nice to have you in here. Yeah. So I
Yeah,
guess
thank you so much for the invitation.
I think that it is 6:30 in the early morning. Yeah, I think that it is very.
I think you saw the sun was in front of my face.
Thank you very much. I have several questions. So could you please tell us about how to handle the heteropolyacid acid? I think it means that, is it, for example, is it hygroscopic or is it stable under air or something?
No, they are very stable.
Okay. Is it
even in solution? They're dissolved in many pollens such water, ethanol, and more solvent, but they are stable in these in all of them.
Okay, is it hygroscopic or not?
No.
Okay, good.
But commercially, there are with the hydrated salt is the compound hydrated, but no, it's not hygroscopic.
Okay, the second one, if you would like to achieve easier separation, I think that you may try by supporting your heteropolyacid acid into the magnetite, perhaps?
Into?
Magnetite. Yeah.
Yes, there are many studies with use the magnetite. Some research in our in Syndeca prepare this compound with heteropolyacid, and the results are very good, and the separation process is easier.
Yeah. I think that's all from me. Thank you. Thank you.
Thank you, Dr. Idham, for the question. Is there any other question from other participants? Okay, it's looked like there is a question from YouTube. Question to Dr. Valeria: whether the catalyst you presented can be used in other green synthesis methods such as sonication.
Yes, I think there are some reports using heteropolyacid with sonication. I didn't test it, but I think that can be used without a problem.
Okay. Thank you. I think that is the last question. For Dr. Palermo, that is the last question for Dr. Palermo, and that's also officially end the last lecture. Once again, thank you, Dr. Palermo, for the information and knowledge that you have shared with us today. Many thank yous. And then to all attendees, after 3 lectures from the 3 remarkable speakers, we have come to the end of today's session. I would like to invite Dr. Idham to give a closing statement. Dr. Idham, time is yours.
Okay, thank you, Mas Fadli, for your kind speech. So I don't want to talk much. Yeah, so this is, as you know, that this is the end of the activities in the World Class Professor Program. So we have started our program in this September. Yeah, September 6th, 2021. I'm sorry. 2021, and then we have performed 7 fine-tuning publication and 4 guest lecture series, and finally we have arrived in the last guest lecture. So thank you very much for Professor Commeiras as the invited world-class professor. And for today's lecturer, we have Professor Banik. Thank you very much. Dr. Valeria Palermo. yeah, from Argentina. Thank you very much. Yeah, you have spent the time in the early morning. Thank you again. And last but not least, thank you for your attention. And we hope that our activities gives a beneficial for you, yeah, for your career, for your professional activities. Yeah, I hope that perhaps in the future we can work together, or we can meet in another session. So good luck for you all. Yeah, hope to see you again. Yeah, thank you very much. Good luck for you. Good afternoon. Yeah. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Idham, for the comment on today's event. Before we officially end today's event, I would like to invite Professor Quatriana to give a closing speech. Professor Quatriana, the time is yours.
Okay, thank you. Can you hear me?
Yes.
Yeah. I'm sorry, I am in a factory right now, so it will be crowded in the noise. So, good morning, ladies and gentlemen. I believe that during this lecture, all of us have tried a fruitful discussion, as I followed just before. In this world-class professor program this year, whose main theme is a green chemistry approach for efficient synthesis of nitrogen heterocyclic compound, we have learned a lot from all speaker sessions delivered by the amazing professors who have shared their interesting work and expertise. And once again, on behalf of the Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, thank you very much for all of you, especially for delivering such important material, so that all of us can deepen our knowledge about this field of research. I'm actually not a chemist, but a physicist, so it will be different, and some topic will be interesting for us also in another fields. So, in this opportunity, I would like to thank the speakers, Professor Dr. Luron Kamaras from Aix-Marseille Universitas, France. It's very nice course. And then Professor Bimal Krishna Banik from Prince Mohammad bin Fahd University, Saudi Arabia. And finally, Dr. Valeria Palermo from Universidad Nacional de Plata, Argentina. And thanks also participants who have joined this lecture from all over the world. I sincerely hope that all of us can contribute to solving the related problems in our own countries after this lecture. So finally, I would like to thank all the committee members, especially Dr. Mohammad, Idham, Darussalam, for organizing this lecture. It's very good. I do also hope that we can meet again next opportunity. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you.
Thank you, Professor Kuat, for the closing speech on today's event. And that also officially closed today's event. To all attendees, please fill the feedback form on the link sent by our committee in the chat box, so that committee can send the e-certificate to you. On behalf of all committees, I would like to sincerely thank you to everybody that has participated in our event. Thank you very much, everybody, and I hope to see you in the next occasion. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you.
Thank you very much.
Thank you.
Thank you. Gracias.
Gracias.